population. So let's start off slow in the morning, or at least for my case. I need to. So overview, so I work at the Paris Observatory for a Marie Curie postdoc, primarily working with FRIPON data. I don't have to really go into the specifics of this camera network, but for this project, we'll be using observations from FRIPON and from where I did my PhD, the Desert Fireball Network in Australia. Using these observations, these are both all-sky fisheye lens systems, and whenever we have observations from these cameras, this is what we get when we see a fireball. If we have enough of these observations, of course, we can stitch them together to try to reconstruct the trajectory as it was traversing the atmosphere, as you can see in this fireball in South Australia. With enough of these observations, we can start to put together what does the small body environment, the meteoroid environment, look like in near space. So this is just showing all the fireballs observed by the DFN during my PhD, with obviously all the green points being the meteoroids, and then you have obviously the inner solar system, Jupiter, etc. So the goal for these networks, and really the goal for the DFN during my PhD in FRIPON, is to try to understand the sources of meteorites. We can look, even when we don't recover a meteorite, we still have all this orbital data, and what can it really tell us? What are the source regions? What are, obviously you could see here, there are some streams that we observe with the DFN. But today I'll be talking about a very specific source region in which I argue you can use the dynamic stability and chaos in order as a very diagnostic characteristic. And that source region is Jupiter family comets. So Jupiter family comets, like this very well-known, well-observed Churyumov-Gerasimenko, which was visited by the Rosetta mission. These Jupiter family comets, or otherwise known as short-period comets, have obviously shorter periods and are known to, or believed to come from the trans-Neptunian region, and have evolved into the inner solar system due to a series of chaotic close encounters with Neptune and then Jupiter, hence the name. You can characterize these bodies and characterize what is a comet, what is an asteroid, what is the middle. Obviously, there's a full spectrum of that, but you can characterize these bodies physically and dynamically. And in the study, we'll primarily focus on this dynamic aspect to try to understand what the contribution is. And the reason why is because for Jupiter family comets, they have a very distinct history. Their dynamics are very strongly connected to these chaotic scattering events with Jupiter. So as you can see in this simulation, graciously donated by Jeremie in the front row, for another Jupiter family comet 45P, you can see over even just a 100-year time scale, you have particles generated to try to understand the meteor shower associated with this body. And you could see how these particles, how their orbits diverge extremely quickly on a 100-year time scale. So brief overview, sorry, not too much text, but let's get through it. So, like I said, these comets are have very unstable orbits. They're very chaotic. So one way to measure this level of chaos is a Lyapunov lifetime, a Lyapunov characteristic exponent. All that means, Lyapunov lifetime means the lower the value, the lower 50 years, it means after about 50 years, you can't very precisely predict where that object's going to be. So, and these values tend to concentrate towards 150 to 150 years. Another thing is, like I said, because of this chaos in the population, the dynamic lifetime of objects within this population tends to be shorter than average. 10 to the 5 years doesn't sound like shorter than average, but just trust me for the case of a 12-minute talk that it is. But the curious thing is that of the Jupiter family comet population, so they're coming from the trans-Neptunian region, not many make their way down to the inner solar system. So to try to search for these bodies within a fireball data set, you're already looking for, if it's coming from that population, they are the weirdos, like inherently. So of the bodies that are coming from this population, around 30% reach the active region being less than 2.5 astronomical units. That rough area is important because around that distance, that's when you start to get some sublimation of water ice. And then to get into the near-Earth region, based on simulations done primarily by Levison and Jones, 1994, 1997, you can search it later, but around 1% or less than 1% of these bodies reach it down to the Earth-crossing region. So very inherently the strange ones, if we're going to see them. There was a study by another scientist, Fernandez, that has done a lot of work on this and found that looking at the dynamics of near-Earth objects on similar orbits, they found, and looking at Jupiter family comets on similar orbits, they found that there was a significant portion that were coming from stable orbits. And it was partially these studies that kind of inspired this work. And then during my PhD in Australia, we examined 50 fireballs, and we found that a lot of them were very stable, but we're trying to go further here. So how do we do that? So in this study, we not only examined the fireballs we observed with the DFN, we augmented it by adding more data that we have collected, along with data that we could access through the literature or through the FRIPON network during my postdoc. So in total, I looked at 646 fireballs and 661 JFCs. So 661 JFCs is all the JFCs that we have observed according to NASA Horizons database. And you could see, trying to get through this quickly, this is just the semi-major axis versus eccentricity. And you can see in the top right corner, so we have DFN, EFN, FRIPON, and MORP data. And inherently, these are only barely overlapping with the JFC population. The JFCs are being these squares. So they only overlap with here, this region, because that's the region that is Earth crossing. So how do the dynamics look? So we calculated the Lyapunov lifetimes and the minimum orbital intersection values. How close does their orbit get to Jupiter? And we find for the Jupiter family comets, we expectedly see that they have very low moid values and tend to concentrate towards around 100 Lyapunov lifetimes. When looking at the fireball data, we see quite a different pattern. You see a much more dispersed group of data. This is all data using Tisserand parameter between 2 and 3 to identify the fireball data. So as we could see, using the Tisserand parameter to identify Jupiter family comets within the fireball data is not really doing a great job, which we kind of expected. Using a more complex criterion that Tancredi came up with in 2014, we see that this is a complicated plot, but basically only 35% are actually fulfill his criterion of those that filled the TJ between 2 and 3. So pretty consistent. Looking at our orbital simulations, so we generate a bunch of clones within the orbital uncertainties, propagate them 10,000 years, and see what happened. For the JFCs, a lot of them leave this active region very quickly. So they get above 2.5 AU within the simulations very quickly. And these are for ones that weren't already starting above 2.5 AU. Don't worry. For the fireball data set, once again, we see most of them stay within the active region much, much longer, mostly for the entirety of the simulations. Curious pattern. Probably a reason for this stability is we see a lot of the objects are in a Kozai resonance. What I mean by that is so you have the argument of perihelion on the x-axis, inclination here, and you see with the fireball data, it goes up, and you have this curve. So whenever it is at high inclination, it's not plotted here, but this is at lower eccentricity, and you see that these objects are basically, whenever they're aligned with the argument of perihelion of Jupiter, which is around here, which is the ideal location to have a close encounter, they're going to be on lower eccentricity orbits and higher inclination. Not really ideal for a close encounter, which is probably why they're stable. If we're looking at the showers, we found a very curious pattern. So this plot is the longitude perihelion, basically the orientation of the orbit for those who are not as familiar, and the inclination of the orbit. Highlighted some major showers that we've identified, and you can see the color is indicating basically what percentage of the clones get out of the active region, red being more chaotic. And we see that with the exception of the draconids, all of the showers tend to be very stable, actually. Using data from EFN, they calculated the PF, the pressure factor, which is an indication of strength based on the ablation characteristics we observe in the atmosphere. With this end being weaker, this end being stronger, we do see that based on the dynamics, that the ones that are more chaotic tend to be weaker. And the difference between these distributions is statistically significant. However, if you only use strength, say, without knowing the dynamics, and you calculate the PF factor within this specific population, just because there are so many stable objects, if you said, oh, it's actually pressure factor class of 3, within this population, based on these 4 subsets, the probability is still likely to be more stable. And that's more of just a Bayesian problem, that the population size is so much larger. Yeah. So getting through the results very quickly, because I'm slightly over time, we find that the Lyapunov lifetimes are consistent with previous studies. They're very short. And we find that 22% of the JFCs in near space are on very stable orbits, which is very interesting and also consistent with previous work. Fireball results, we find no Lyapunov lifetime concentration, only 35 fit the Tancredi criterion. And the big takeaway is, based on our analysis, only about 1 to 5% of the data sets are dynamically consistent with JFCs. It doesn't necessarily mean that the 1.5 or 1 to 5% are coming from comets. It's more of 1 to 5% are coming from pristine samples, very likely coming directly from the Jupiter family comet population. A lot of these stable objects have very similar characteristics to some asteroids from the main asteroid belts, but they also have very similar characteristics to Marsden and Machholz-like comets. So those objects are the key for understanding the population. Thank you.
Okay, thank you very much. Questions in the audience? Yes, Yuri.
Thank you, Patrick. Nice work. I have a question for the final results. Only 8 to 20% being cometary dynamically. It's the 20% from the whole sample of the 600 or from the reduced sample according to Tancredi?
Yeah, that's 8 to 21% of the sample we analyzed. So 8 to 21% of the TJ between 2 and 3 for the 4 data sets. Yeah.
Okay, thank you.
Okay, I think we have to move to the next talk. So we thank again Patrick.